Okay, folks. Number one. I wanted to remind everybody, because it has been a couple of weeks, that there is a homework due tonight. The homework is over stoichiometry and solutions. I wanted to remind everybody, because it's been a couple of weeks, that I do have office hours today from 3 to 4:30. The next thing I wanted to let everybody know is tomorrow's lab is the thermodynamics lab. I realize we have not gotten to thermodynamics. So I will, at the start of class, walk you through basically how you're going to be doing the mathematics associated with the lab. We won't get to thermodynamics until next week, but I will have the thermodynamics lab due next week, even though we won't have completed the thermodynamics chapter next week. We will have it due next week. Again, I will walk you through the math, though, at the start of lab. So be prepared to take some notes so you know how to do the mathematics for yourself. And then you should be okay from there. The next thing is Thursday, you do have a quiz. It's an active quiz like normal. It's due by 11:59 p.m. Again, it's going to be over stoichiometry and solution calculations. Now, heads up for next week. You will have a homework, you will have a quiz next week. But you will also have 2 labs due next week. You will have one of them due on Tuesday. The lab that will be due on Tuesday, each person will turn in their own lab. It will be done on active. It is the lab that we did prior to spring break. It is the reactions lab, and all of the data that you need to input is going to be on active. And each person submits their own reactions lab. The second lab due next week is, as I've already mentioned, the thermodynamics lab. It'll be due on Thursday of next week. Sometime this week, I plan to post your bonus points, because all bonus point opportunities are finished. Remembering that you can get a maximum of 20 bonus points towards the semester. So I will post that sometime this week. Other things that I will get posted sometime this week. Number one, I will post a blank copy of exam 3 and the key so you can compare and make sure that I didn't make any mistakes. Number 2, I have not had a chance to post homework answer keys because I want to redo them. I don't trust the answer keys I have from the past because I know there are mistakes, so I want to redo them. I will be getting those posted this week, along with practice problems associated with what we're discussing. So lots and lots of things are still to come. Any questions for me? Ashley. The week prior to finals. I think it's on Tuesday so that I can get them graded, but I don't remember. You are not turning in the printed out version of your reactions lab. That is correct. It is strictly on active. Other questions? Everything that I just discussed is on Blackboard, but I wanted to make sure that I mentioned it verbally. I think there's still a couple of people I don't think this class is very bad. My other class is horrible about checking Blackboard. I think this class is pretty good about it. So. But just in case. Any other questions before I get into today's material? Okay, so what I'm going to be doing today is I'm going to be discussing precipitation reactions and acid-base neutralization reactions. As I discuss precipitation and acid-base neutralization reactions, we are going to, number 1, predict the products. Number 2, balance the chemical equation. Number 3, determine the state of matter for every single compound in the balanced chemical equation. Number 4, use the balanced chemical equation to develop the complete ionic equation. Number 5, use the complete ionic equation to develop the net ionic equation. As we're doing all of this, we are going to apply the solubility rules that I discussed on Thursday of last week. We are going to apply our knowledge of strong acids compared to weak acids and strong bases compared to weak bases that I discussed on Thursday of last week. And ultimately, you've got to apply those solubility rules and the definition of strong acid, strong base, so you know who's a strong electrolyte, because that's going to come into play. So, to start with, precipitation reactions and acid-base neutralization reactions are metathesis reactions. Basically, folks, they are displacement reactions. Now, precipitation reactions can actually fall into two categories. All a precipitation reaction means is that a product is a solid precipitate. This can come from a double displacement reaction, where the cations swap their anion partner. Or it can be through a single displacement reaction, where the cation is exchanged for an element. I am going to focus most of my attention on this double displacement reaction. So in the laboratory, the reactions laboratory, you reacted potassium iodide with lead 2 nitrate. I want to say this is the second one you did in the reactions laboratory. Now, what I see is I have an ionic compound reacting with an ionic compound. And a lot of times when we react two ionic compounds, we're going to be doing a precipitation reaction. Meaning the cations are going to swap their anion partners. So the first thing I'm going to do when I see, oh, I have two ionic compounds, is I am going to take those compounds and I'm going to think about the ions that those compounds came from. Potassium iodide came from potassium ion and iodide ion. Lead 2 nitrate came from lead 2 plus ion and nitrate ion. So again, when I see two ionic compounds, I'm automatically going to say, okay, it's probably a precipitation reaction. And I'm going to take those ionic compounds and I'm going to think about where those ionic compounds came from, the ions that they came from. Now, because I'm thinking, oh, this is probably a precipitation reaction, it means that I'm going to say, oh, this is probably a double displacement reaction. So the cations, potassium and lead 2 plus, are going to swap their anion partners. So the potassium is now going to react with the nitrate, and the lead 2 plus is going to react with the iodide. Now, one reason I take this time and go, okay, what ions did they come from? And I swap the ions around is so that I can determine what is the chemical formula for the product. What would be the chemical formula for a compound made of potassium ion and nitrate ion? It would be KNO3 in a 1-to-1 ratio. What would be the formula of a compound made from lead 2+ ion and iodide ion? TBI2. Notice I didn't take what was here and simply move it. You cannot take what is in the reactants and simply move it. You have to go back to the ions and move the ions around. Because the quantity of the ions is dependent upon who it is combined with. So you can't simply just pick things up and move them. You got to go back to their original ions and move the ions and then determine what the formulas are. Because the quantity of each is dependent upon who it is reacting with. Now, once you have your, so what we did just now, folks, I told you a list of things I was going to do. What I just did is I predicted what the products of this reaction are going to be. And the way I predicted it, or the reason I knew how to predict it, is because this is likely a precipitation reaction because I have 2 ionic compounds, which means it's likely a double displacement reaction. So I swapped the anions the cations were attached to. Now I need to balance this thing. To balance this equation, you need 2 potassium nitrates and 2 potassium iodides. That was the second thing I said we would do. The third thing I said we would do is figure out the state of matter. Because these are ionic compounds, you use your solubility rules. Rule number 1, if it contains a group 1 metal or ammonium, it is soluble. There are no exceptions. So potassium iodide is soluble without any exceptions. Potassium nitrate is soluble. There are no exceptions. There are no exceptions because potassium's in group 1. Rule number 2, nitrates, acetates, perchlorates are soluble, no exceptions. But so this means that potassium, lead 2 nitrate is soluble because it contained the nitrate. You will notice that rule number 1 and rule number 2 knocked out 3 of 4 compounds. The rest of the rules are about the anion. Rule number 3 says Chlorides, bromides, and iodides are soluble, but there were 3 exceptions to that rule. One of those exceptions being lead, meaning that this is a solid. In the laboratory prior to spring break, if you read what you wrote, you saw potassium iodide was a colorless solution. You saw that the lead 2 nitrate was a colorless solution. And when you combined the potassium iodide with the lead 2 nitrate, a yellow solid was formed. That yellow solid we can now predict was lead 2 iodide. We were able to predict that using the solubility rules. So now we've just done the next thing I said I would do, which is basically what we just did is we developed the balanced chemical equation, including the states of matter. Now to get to the complete ionic equation. If you go back to what I said on Thursday, the difference between the balanced chemical equation and the complete ionic equation is that you separate all strong electrolytes. So now I need to determine who is a strong electrolyte and who is a weak electrolyte. I later told you that the strong electrolytes are soluble ionic compounds and strong acids and strong bases. Since we're working with ionic compounds, specifically, I'm going to be looking at the soluble ionic compounds. Meaning I'm looking at the aqueous ionic compounds. So in other words, potassium iodide is going to be a strong electrolyte. Lead 2 nitrate is going to be a strong electrolyte. Potassium nitrate is going to be a strong electrolyte. Those are all strong electrolytes because they're all soluble ionic compounds. The lead 2 iodide is a weak electrolyte because it is an insoluble ionic compound. And if you look under the weak electrolytes, that was one of the weak electrolytes. Now to get to the complete ionic equation, we have to dissociate all strong electrolytes into their ions. Folks, there's another reason to write out the ions in this format. Because when we are taking these strong electrolytes and dissociating, we're going to put them in this format. So, the Ki, being a strong electrolyte, is going to dissociate into K plus ion and iodide ion. The state of matter of the ion is going to be the same as the parent compound. So since the parent compound is aqueous, the ions are going to be aqueous. Now, according to our balanced chemical equation, we have 2 potassium iodides, meaning you have 2 potassiums and you have 2 iodides. The lead 2 nitrate is going to dissociate into lead ion and nitrate ion. The ions will have the same state of matter as the parent compound. So since the lead 2 nitrate is aqueous, the ions are aqueous. Now, to make our ionic compound charge neutral, we needed 2 nitrates. That 2 becomes the coefficient in the complete ionic reaction. We also have to dissociate our potassium nitrate. Again, it makes potassium ion and nitrate ion. The state of matter of the ions is going to be the same as the parent compound. So since potassium nitrate was aqueous, the potassium ion is aqueous and the nitrate ion is aqueous. The coefficient of 2 means I have 2 potassium nitrates. So I have 2 potassiums and I have 2 nitrates. You only, now, lead 2 iodide is a solid. It is a weak electrolyte. When going from the balanced chemical equation to the complete ionic equation, you only dissociate these strong electrolytes. So we're not going to touch that weak electrolyte. We're just going to bring it straight down along with its state of matter. And that is the complete ionic equation. Folks, what this says to me is that in that clear, colorless solution of potassium iodide, what you really had was potassium ion and you had iodide ion. You didn't have Ki. In that clear, colorless solution of lead 2 nitrate, what you really had was lead ion, and for every 1 lead, there were 2 nitrate ions. You didn't have PbNO3, 2. You had these ions. Now, when you dropped them together, that yellow precipitate was PbI2. But there was still color, there was still some solution. It wasn't just all solid at the bottom. It was still in solution. Well, in that solution, you still have potassium ion and nitrate ion. That's what this means. That's what this is telling us, is what does everything actually look like in solution? Now, if you can get to the complete ionic equation, going to the net ionic equation is easy. All you do is remove any substance that looks identical on the reactant side as it does on the product side. These are called spectator ions. You remove anything that looks identical on the reactant side as it does on the product side. Therefore, I will be removing the potassium because the potassium looks identical on both sides. I will be removing the nitrate because the nitrate looks identical on both sides. The only thing that goes into the complete ionic is what is left over. So the 2 iodides will be moved into the complete ionic. the lead 2 plus will be moved into the complete ionic. And into the net ionic. And the lead iodide will be moved into the net ionic. That is because going from the complete ionic to the net ionic, we remove spectator ions. That is because what a net ionic equation tells us is what undergoes a change. I'm letting everybody get this down, and then I'm going to review it where you can listen and not write. Because there's a lot of little bitty details in that story. So don't go to sleep on me just because I'm retelling the story. There's a lot of little details, and I don't want you to miss those little details. First thing, I noticed I was working with 2 ionic compounds. 2 ionic compounds, to me, means double displacement. So I took those 2 ionic compounds and I reverted them to their ions so that I could do the double displacement. Meaning the potassium swapped its anion for the nitrate. The lead 2 swapped its anion for the iodide. Once we swapped the ions, we then created the formula for the compound that would have been generated based off of those ions. The next thing I did was balance the chemical reaction. After that, because these were ionic, I used the solubility rule to determine the states of matter. Rule number 1, anything with group 1 is soluble. So group 1, soluble. Group 1, soluble. Rule 2, anything with nitrate, acetate, or chlorate, soluble. Nitrate, soluble. Technically nitrate, soluble. But once you've assigned a state of matter based off of rule 1, you don't have to pay attention to it again. Once you've assigned a state of matter off of rule 2, you don't have to pay attention to it again. That left only one compound I had to figure out. So I looked at the rule for iodide. And the rule for iodide says chlorides, bromides, and iodides are soluble except for lead 2 plus. Since that was an exception, that means that that's a solid. So we determined state of matter. The next part of the story was to take a balanced chemical equation and convert it into the complete ionic equation. And yes, folks, when you do this conversion from the balanced chemical equation to complete ionic, I do expect states of matter. I do expect coefficients. I expect all of that, as does active. Now, to go from the balanced chemical equation to the complete ionic, I determined who the strong electrolytes were because you only dissociate the strong electrolytes. So, potassium iodide had to be dissociated. Notice it got dissociated into its ions. The state of matter for the ions is the same as the parent. The fact that there are two KIs means that there's two molecules of Ki. So that means that there's two potassium and two iodides. Lead nitrate, because it was a soluble ionic compound, means it's a strong electrolyte. So it's going to dissociate into its ions. Notice that I did not just bring down NO3 2. That's not an ion. NO3 subscript 2 is not an ion. NO3 is an ion. Again, the ions have the same state of matter as their parent, and this 2 is there in order to make this compound charge neutral. That 2 became a coefficient when you moved it to the complete ionic equation. So notice what becomes coefficients in the complete ionic equation. Prior coefficients and subscripts that are there to make a charge neutral compound. Those become coefficients when you get to the complete ionic. Potassium nitrate got divided into its ions. The state of matter is aqueous, just as the parent. And there were 2 of them, so that's why each ion got a 2 before it as its coefficient. And then finally, lead iodide. Lead iodide is a solid. It's a insoluble ionic compound. Therefore, it's a weak electrolyte. That's why it's stated as a unit. Once you get to the complete ionic, the net ionic's a breeze. You remove the spectators. So I took out potassium because it appeared the same on both sides. I took out nitrate because it appeared the same on both sides. And that left me with what underwent a change. The other thing I want to note, because I do see students do this, don't break up your polyatomic ions. Don't break them into their elements. Polyatomic ions are ions. They come as a unit. Questions about the story now that you've heard it a second time and didn't have to write while you were trying to hear it?
I forgot whether you told us. Do you want us to remember the solubility rules?
You do not have to memorize the solubility rules for the exam. You will be given those. You do have to memorize your strong acids and know who your strong bases are so that you can distinguish between a strong acid and a weak acid, and a strong base and a weak base. You will treat, so there was another reaction that you did in lab, which was FeNO3 3 plus NaOH. That reaction is going to be the same, or is going to be treated similarly to what we just did. Looking at this, that means that the ions are iron 3 plus and nitrate. And the other ions are sodium ion and hydroxide ion. I will give you that much, but I expect you to do the next part of it. So that was like number 8, I think. Of the lab. Okay, but what I want to do is I want to deal with an acid-base reaction. So in the laboratory, you reacted hydrochloric acid with sodium hydroxide. First thing I notice is that this is a strong acid combining with a strong base. So this tells me that it is an acid-base neutralization reaction. An acid-base neutralization reaction will always have water as one reactant. And a salt as the second reactant. I meant product. Thank you. Water as a product and the second product. Now, this salt will always be the result of the cation of the base reacting with the anion of the acid. Because, folks, this is again a double displacement reaction. So we need to divide this into our ions. So our ion up here was hydrogen and chloride. For our base, it is sodium and hydroxide. One of the products will always be water, and the other product will be a salt that comes from the cation of the base and the anion of the acid. So in other words, this one will be sodium chloride. Folks, one thing that will help, I mentioned it when balancing a chemical equation, but now you can see it. This being a double displacement reaction, I said, when you see water, think of it as HOH. That's because if we're dealing with an acid-base neutralization reaction, that water came from the H and the OH. So that's why you can think of it that way when you're trying to balance the chemical equation. Second step, after you do the double displacement reaction, is to balance the equation. It's balanced in this case. Third step is to determine the state of matter. Which we haven't discussed, but Your acids will be aqueous. The bases, you will use your solubility rules. Water, will be a liquid. And the salt, you use your solubility rules. I'm going to rewrite that equation so that we can see it for the next piece. Okay, so using the rules, our acids are going to be aqueous. Our base, we use the solubility rules. Well, oxides and hydroxides are soluble if they're mixed with group 1. Group 1's always soluble. The water will be a liquid. And the sodium chloride, you'll use the solubility rules. Well, group 1's always soluble. So this is your balanced chemical equation using with the states of matter. A moment ago, I said this was a strong acid and this is a strong base. What type of an electrolyte are each? Strong electrolytes. What about water? It's not listed there, folks. It's not listed as one of your strong electrolytes. It's not listed as one of your weak electrolytes. So I said anything that's not listed as a strong electrolyte or a weak electrolyte must be a non-electrolyte. What type of ionic compound is sodium chloride? Well, we said it's soluble. So it's a soluble ionic compound. So what type of an electrolyte is it? Strong electrolyte. Now that you've assigned strong electrolyte, weak electrolyte, non-electrolyte, now we can actually go in and do a complete ionic equation. We're going to develop the complete ionic equation by dissociating everything that's a strong electrolyte. So hydrochloric acid, because it is a strong electrolyte, gets dissociated into hydrogen ion and chloride ion. The ions have the same state of matter as their parent. Sodium hydroxide gets dissociated into sodium ion and hydroxide ion because it is a strong electrolyte. The state of matter will be the same as the parent. Water, being a non-electrolyte, is pulled straight down. Sodium chloride, because it is a strong electrolyte, gets dissociated into its ions. The ions having the same state of matter as the parent. That is your complete ionic equation. Now to get from the complete ionic equation to the net ionic equation, you remove your spectators. Sodium is a spectator because it looks identical on both sides. Chloride is a spectator because it looks identical on both sides. You bring down anything that's not a spectator into the net ionic equation. And you get H plus OH minus equals water. You may want to make a note and star it with what I'm writing right now. No matter what strong acid I use, no matter what strong base I use, if I do a strong acid, strong base neutralization reaction, the net ionic is H plus OH minus goes to form water. So folks, I could do sulfuric acid and sodium hydroxide. Sulfuric acid is a strong acid. Sodium hydroxide is a strong base. That makes its net ionic this. I could use sulfuric acid and potassium hydroxide because I got a strong acid and I got a strong base. The net ionic is this. Strong acid, strong base, that's your net ionic. If I bring in a weak acid or a weak base, that changes things. It also changes, you notice I didn't say calcium hydroxide, strontium hydroxide, or barium hydroxide. That is because those behave a little differently. Because if you'll go back to the solubility rules, I said they're only slightly soluble. Yes.
So is knowing whether something is a strong acid or strong base simply like memorization, or is there? Okay.
Well, for the strong acids, yes. For the strong bases, they're going to be soluble ionic compounds. I don't have time to do one today, But as we will see at the start of class on Thursday, this is not gonna be true if it's a weak acid or if it's a weak base involved. If we change one of these from strong, that statement is no longer true. So again, folks, the story. Had it. And this was number 5, I believe, on that reactions lab. I just walked you through all of number 5. I told you to bring the lab because I was going to walk you through them, or at least some of them. But basically, this story started out with a strong acid, strong base. As soon as I saw I had strong acid, strong base, I automatically knew that one of the products, or basically, as soon as I saw I had an acid and a base, where the base had hydroxide specifically. In other words, as soon as I saw I had an areneous acid and an areneous base, I knew one of my products was going to be water and salt. Because I knew this had to be an acid-base neutralization reaction. Any issue with that statement I just made? The areneous acid is a proton donor. The areneous base has to have a hydroxide. Because this was an areneous acid and areneous base, I knew that I was going to get water and a salt because it was an acid-base neutralization reaction. The state of matter, strong acid, is aqueous. This is an ionic compound, so I used the solubility rules and found out it was also aqueous. Water is always a liquid. The salt is going to be an ionic compound, so I used the solubility rules, found out that it was aqueous. Strong acids are strong electrolytes. Strong bases are strong electrolytes. Soluble ionic compounds are strong electrolytes. But liquids and gases, solids, pure liquids and pure gases are going to all be non-electrolytes or weak electrolytes. To go from the balanced chemical equation to the complete ionic equation, I separated anything that was a strong electrolyte into its ions. So the hydrochloric acid was separated into hydrogen ion and chloride ion. The sodium hydroxide was separated into sodium ion and hydroxide ion. The sodium chloride was separated into sodium ion and chloride ion. Then to go from the complete ionic to the net ionic, I removed spectators. Spectators being things that appear the same on both sides. And so I was left with H plus OH minus goes to form water. Any questions? So what am I going to do on Thursday? Well, I want to do a weak acid, strong base, neutralization reaction so that you can see how they differ. Number 1. Number 2, we are going to start dealing with redox reactions. And to discuss the redox reactions, I will be doing single displacement reactions, such as the magnesium with hydrochloric acid. And the copper sulfate with iron. Yes, copper sulfate with iron. I will help you through those, which will get you another couple of your problem sets. Any questions for me? do me a favor and go ahead and watch the redox reaction video before Thursday, the flipped classroom video. And the reason I'm asking you to do that is I would like you to go ahead and take notes on the redox, the oxidation rules, so that I don't have to write out all the oxidation rules. Or you don't have, I'll actually already have them written out, and that way you don't have to copy them. Questions? Otherwise, I will see you in lab tomorrow for our next to last lab of the semester. Alternate twice.
I was like, here between Wendy and.
Yeah, like, that's what you should have done.